Hey guys, welcome back. We're doing exponential functions for today. We're going to look at how they come about, the general form, and then a few examples of how to use them. Okay, so starting off, we're just going to go through what is an example of an exponential growth. We've got a culture of bacteria, and it starts at weight of 20 micrograms, but increases its mass 30% every 10 minutes due to the bacteria multiplying. So, it starts out at 20. We have the number of 10-minute time periods increasing, so it's 0, 10 minutes, 20 minutes, 30 minutes, all the way to 60 minutes. The growth ratio doesn't change in each case. It's always that increase of 30%. So how does this look over the 6 time periods that we have here? 7 rather. Starts out as 20. Our next time period is going to be that increased by 1.3. I won't actually do these calculations until I get down to 60 minutes. I just want to see how this function or how this rate of growth changes. Okay, this 20 times 1.3 after the next time period becomes 20 times 1.3 twice, times 1.3 times 1.3, or 20 times 1.3 squared. Okay, I'm going to have to squeeze this back a little bit. Maybe not. For the next time period, it's increased again by 1.3, so 20 times 1.3 squared, where it was at the end of the second time period. Okay, and then increased by another 30%, which means we get 20 times 1.3 cubed, because our index laws say that once we have the same base, then we can add the powers. 2 add 1 is 3. Alright, same thing again. If we multiply by 1/3, that power on the 1.3 increases by 1. And again, it would increase to 5 and 6. Each time we've multiplied by 1/3. Each time we've had that next increase in time period, we've increased that power of 1.3 by 1. Okay, so we can see this pattern of just increasing that power. This, when you actually work it out, becomes approximately, and I'll use this squiggly equals, approximately 92.5. Right. So our 20 micrograms suddenly becomes 96.5 micrograms. And that's quite a big growth. It's almost 5 times what it was in an hour. It's pretty crazy, but it's a small number, 30%, but it's increasing so often. Anyways, this formula, or the function that it follows, looks a little bit like this. The mass function with respect to t, where t is the number of 10-minute time periods, is equal to 20 times 1.3. How that 1.3 is our base, it doesn't change, that's our rate. Okay, and the variable, the number that does change throughout that function, is actually the exponent. Okay, so you can see that that's that pattern that you see. Even at 0, it'd be 1.3 to the power of 0. This becomes 1 anyway. So 20 times 1 is 20. So it's consistent right the way through. So this mass function clearly is an example of an exponential function, which is why we brought it up. Okay, that variable is the exponent. In general form, it looks a little bit like this. The function of x is equal to b, which is our base, I guess, raised to the power of whatever my variable is. Okay, that's the simplest form. Okay, and we want where b is not equal to 1, because then you don't really have a whole, you don't really have much of a function. You just have a horizontal line. Okay, that's our general form. That is what an exponential function looks like in general. So, that base, that number with the variable as its power, helps us to indicate that rate of change. Okay, if we had 2 as our base, this means that as x increases, each increase of 1 in x means that whatever that number is doubling. It would go 2, and 2 squared is 4, 2 cubed is 8, and it just doubles and doubles and doubles and doubles. Alright, because that's what that base is telling us. This would be an increase of 40%, just like we saw the 30% in our previous example. But when that number is less than 1, then we actually have what we call decay. These are examples of growth. This is an example of decay, where this is actually decreasing over time. We're going to look more at exponential functions and their graphs, as well as their transformations in a couple later videos. But for now, let's look at some examples. Okay, so I've made a couple mistakes in the writing of this, but I'll read it out. We're going to take that same bacteria function where we had it starting at 20 and increasing at 30% for every 10 minutes. Okay, the bacteria grows in its mass, in micrograms according to the function mt is equal to 20 times 1.3 to the power of t, where t is the example, where t is the number of 10-minute time periods. So find the mass after 90 minutes. Well, we could ask a similar style of question in lots of different ways. Find the mass after 90 minutes. This means when t is equal to 9. There is 9 lots of 10-minute periods, so we're going to try to find m9, which is 20 times 1.3 to the power of 9. Let's just bring up calculator, which I probably should have done earlier, but right now, just going to take a second to load. More than a second, we'll get there. So while that's loading, let's quickly look at how to solve the other two problems. We don't exactly need the number itself there. Anyways, find the mass when t is equal to 12. Well, that's pretty straightforward. We're just trying to find m12, which is 20 times 1.3 to the power of 12. Wherever t was, we've replaced it with 12. Find m of 3. M of 3 means that, again, we're replacing t with a 3. And now that that calculator is loaded, hopefully we will get some numbers for us. We've got 20 times 1.3 to the power of 9. We've got 20 times 1.3 to the power of 12. We've got 20 times 1.3 to the power of 3. Okay, so now we've got that, this is what it looks like. 212, 465, 43.94, and we're always talking about micrograms in this example. The mass is in micrograms. Okay, so just a quick substitution. We've done similar stuff before. Okay, nothing crazy at this stage. Okay, example 2, we're going to be using our index rules. We've already gone through a bunch of them before. Okay, when we are times in two numbers, then we can, or that have the same base, then we can add the powers. So this just looks like 3 to the 2x take 5. This might be a little bit hard to see. Okay, but we're going to add use a set of brackets so that we don't get any of our negative numbers mixed up, especially when we're taking. Alright, and then we've got, I'll write it a little bit larger because I'm working within the power. We've got 3 to the power of 2x, take 5, add 5, take 3x, which is equal to plus 5 and minus 5 are going to cancel each other out. We're going to get 3 to the x, negative x, or if you prefer, 1 on 3 to the x. Right, that should be right. Yeah. Okay, remember that negative on the x doesn't change the value of the base itself, it just gives it that reciprocal, it flips it. Okay, let's do a more difficult example of that same idea, but we're going to be doing something a little bit bigger. And notice that none of these numbers have the same base, so it's going to be really hard to put them together, right? Well, anytime we have these numbers, we preferably want to express them as primes. Okay, so 15 is the same as 3 times 5. 21 is the same as 3 times 7. 35 is the same as 5 times 7. And 45 is the same as 9 times 5, but 9 is 3 squared. So if we say 3 squared times 5, then we should be able to get these numbers. So let's express our problem using each of these changes in these numbers. So we've actually got 3 times 5 to the power of 4i take 5 times by 3 times 7 to the power of 2i add 1 over, try that again. Five times 7 to the power of 2i take 2 times by 3 squared times by 5 to the power of 2i take 3. Alright, so we are going to, if we have powers on the outside of brackets, then that power is going to multiply the powers on the inside. This is going to get quite large, and I'm already running out of room on this page, so bear with me. We're going to have 3 to the 4i take 5 times 5 to the 4i take 5 times 3 to the 2i add 1 times 7 to the 2i add 1 all over 5 to the 2i take 2 times 7 to the 2i take 2 times 3 to the, because we've got 3 squared here, we've got 2 times 2i take 3, so we're actually going to have, I'll write it like this first. Okay, something like that, and then 5 to the 2i take 3. Now anything that has the same base, we can start to add or subtract their powers. Okay, we've got a few 5s, we've got a few 3s, and we've got a couple 7s. Okay, let's work on the 3s first. So we've got, just got a different color pen. These 3 here. 3 to the 4i take 5 plus 2y plus 1 take all of this. So 4i take 5 plus 2i add 1 take 2 lots of 2i take 3. That's just the powers of 3's. Okay, and just in case, I'm going to chuck a little set of brackets around that one as well. Let's go with the 5's. We'll deal with the actual simplifying in a second. Alright, we're going to have times 5 to the 4i take 5 plus, take 2i take 2 take 2i take 3. Okay, because when we're dividing by a number, then we take the power, well, if they have the same base. Alright, and going up the page a little bit here with number 7, this is continuing on, so it's not a new line as such. We're going to have 7 here and here, whilst 2, it's going to be 7, 2i, add 1, take 2i, take 2. This is why using brackets is going to be really important, because we're going to be taking 2i, but then we're going to be adding 2. I'll keep this nearby. Yeah, that works. Alright, so this is going to be equal to 3. We've got to simplify all this. So 4i take 5 plus 2i. Let's expand and simplify, I suppose. 4i take 5, add 2i, add 1, take 4i, take 3. Add 6. Yeah, that's better. And we're going to have the 5's. 4i take 5, take 2i, add 2. We're going to have that negative 2. And then take 2i, add 3. And lastly, the 7's. 2i, add 1, take 2i, add 2. Okay, there's that one now. Final cleanup, collect like terms. Uh, 4i plus 2i, take 4i, 4i and 4i cancels, leave it with just 2i, take 5, add 1, so we've got 7, take 5, which is positive 2. 5 to the power of 4i, take 2i, take 2i, which means we've got 0i. Cancel all of these. And then we've got minus 5, add 5, makes it 5 to the 0. Okay, that's easy. 5 to the power of 0 is going to be 1, making that simplified quite well. Alright, 7, 2i, take 2i, so they're going to cancel. Then we're going to have 7 to the power of 3. Okay. We've got 3, 2i, add 2, times 7 to the power of 3. And I suppose you could work out what 7 to the power of 3 actually is. Alright, but that's enough for this example. Okay, so don't forget your index laws. Exponential functions are when that variable is the power, and we have that general form, which you should go back and take a look at. Those are the 3 things that we need to deal with today. If you have any questions, let me know.